Hello everyone, let's find out what is the capacitance of a parallel plate capacitor. Now here, a parallel plate capacitor means the capacitor contains two parallel plates as given here. You can think of the two walls of your room as two capacitor plates. Let the area of each plate be A. That is, area of this plate or this wall is A, and similarly area of this wall should be A, and let the distance between the two plates be some D. So D is the distance between two plates as given here. The distance between these two plates is called as D, but here we have spherical plates, but what we want is parallel plates. Let us connect these two plates to a battery. Because of this, charge will be induced on the two plates. Let charge on this be positive and charge on this be negative. So if charge on this place is capital Q, charge on this would be minus Q. So here we need to find out the expression for the capacitance in this configuration. There is air between the two plates as seen here. So this is a basic diagram. So let's find out the expression in this case. Now let's draw its side view. That is, this was the original configuration where we had two plates and area of each plate was A. Distance between them was D, and we connected them to a battery which would offer a potential difference of V, which means the difference in potential between these two plates would be V. That's the meaning of it. Now this would create an electric field. The electric field goes from the positively charged plate to, it goes from here to the charged plate which is negative. So the electric field goes like this. So the field is here E, and we learned that in case of a uniform field, we know that E is equal to V by D. So this is the form for E. Now let's find out what this E itself is. Now here we assume that the plates are quite big enough so that we neglect the effect of fringing. We saw what it is in the previous discussion. So in this case, if you draw its front view, that is, if somebody sees from the front like this, then what they would see would be two lines like this. Now the charge on this side is positive, on this side of the plate is positive, this is negative. I'm drawing the side view of the capacitor plates. Let's consider three regions called as region 1, region 2 and region 3. So let's find out what is the electric field in each of this region. Before that, if you have a single, say, conductor with charge on one side, example, say charge is positive on this side, we learned that this conductor would create a field in both directions. So electric field go out like this, electric field will be going out like this, and this field is uniform, it goes to infinity, and this field here is equal to sigma by 2 epsilon naught. Similarly, electric field on this side would be the same in magnitude. So even the field anywhere on this side has same value, which is again E is equal to sigma by 2 epsilon naught. The sigma would be charge by area, so it will be charge by area. That is what sigma is. Similarly, if we consider negative plate and the charge is on this side, even this plate, assuming this to be like an infinitely big one, but theoretically and practically we can't have infinitely big plate, but we assume that the plate is quite big enough to neglect the fringing effect. So we saw in theory class that if you have a negatively charged plate, electric field goes into the plate. So the electric field would be towards the plate. The parallel fields, it is towards the plate. It's same thing this side also. The field is towards it like this. So remember, it's like uniform field, and even here this field value would be same in magnitude, which is E is equal to sigma by 2 epsilon naught, but different directions here. With this in mind, we'll find what is the field in the region 1. So to understand this, we'll again draw the two plates. The charge on this plate is positive, the charge on this plate is negative. So we'll take a random point here. We take, for example, point A. This is point A. We want to find what is the field at this point A. Now, because of the positive charge, the field lines will go into the plate, it will go away from the plate. So if you look at this plate, for this point, the electric field because of the positive plate goes out like this. So we have a field which is sigma by 2 epsilon naught. Suppose we call this as plus direction, then this would be negative because this field is against the plus direction. So in terms of direction, it will be negative here. This is what the field would be. Now the field because of the negative charge will be towards the plate. So at this point, there is a field which is going like this towards the negative plate. It goes like this. Even here, the value would be sigma by 2 epsilon naught. So at this point, we have two fields, one going from right to left, that is this one, and from left to right. Therefore, the net field here, if we call as E, say in region 1, that will be this value, which is sigma by 2 epsilon naught minus this value, because it is opposite to it. So sigma by 2 epsilon naught, that is equal to 0. So this is the field in region 1. Similarly, if we look at a region somewhere here, region 3, we take a point, a random point here, say some point R. Even here, electric field because of the negative plate would be towards it. So we have a field which is towards this one, so minus sigma by 2 epsilon naught, because it is against a direction chosen. Now because of the positively charged plate, the field goes out. So field from here will go out like this. It goes out like this, which is positive. So E is equal to sigma by 2 epsilon naught because it goes along a chosen direction. Therefore here also, electric field in region 3 would be sigma by 2 epsilon naught. It will be this value minus of this value. We're adding it basically, but it's minus sign there. Therefore, the field even in region 3 is equal to 0. So the field in region 1 and 3 is 0. So there is no field outside the capacitor plates. Let's find out what would be the field somewhere inside the plates. For this, we'll take a random point here called as point J. Let's find out what is the electric field because of the positively charged plate. So the field line goes out of it. So at this point, the field will be going like this. We call this as sigma by 2 epsilon naught. And because of the minus charge also, the field will go towards the charge. So here, the field goes towards the charge, towards the plate, and even this also will have same value, sigma by 2 epsilon naught. Therefore, in this region here, we get net field. So this net field, we call region 2, is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. It is equal to sigma by epsilon naught. Therefore, the field between the two plates is a constant, and that value is equal to sigma by epsilon naught. So recall that we already have E is equal to V by D. So E is equal to sigma by epsilon naught. Also, E is equal to V by D as seen earlier. So if we equate these two, then we get sigma by epsilon naught is equal to V by D. But sigma was given as charge density, which means it is charged by area. So charge from this will be sigma into area. So, or we can write directly from here only. It will be charged by area because the charge is present in the entire area. That by epsilon naught is equal to V by D. Keep in mind that when I say charge, it is charge on any one plate, not both the places, because if you add the total charge, it will be 0. It will be charge or plus Q minus Q. So when I say charge, it is charge on any one plate, not both the plates. It is equal to V by D. Rewrite this, Q by A epsilon naught is equal to V by D. Now recall that Q is equal to C into V, or C is equal to Q by V. Bring this V down, then Q by V is equal to A epsilon naught by D, but this itself is equal to C. This is what is C. Therefore, finally what we get is, we get C is equal to epsilon naught A by D. So this is the required expression for capacitance of a parallel plate capacitor. Keep in mind here that it depends only on the area, not on its dimensions, which would mean that the form would have been same for any two conductors. That is, whether we have two parallel plates or whether you have two, say, spherical plates, the form is same, which means even here also C is equal to epsilon naught A by D only. So keep in mind that even though we have derived this expression for a parallel plate capacitor, but this form could be used for any two conductors having a certain area. Observe carefully here to understand what does C depend on. As seen here mathematically, C depends on three factors. It depends on epsilon naught, which means it depends on what is the medium between the two plates. For example, in this case, it is air. Suppose if we insert a dielectric between two plates, then it may change. So we'll see next slide. But for here, the capacitance depends on the medium between the two plates. It also depends on area of the plates. So if we take a bigger area, we'll have a bigger capacity or more capacity, and it goes inversely as distance between two plates. So if we bring the plates closer, if we bring this somewhere here, then C would increase. So it depends on epsilon naught A and then D. Even though we have defined Q is equal to CV and we wrote C as Q by V, keep in mind that C doesn't depend on Q and V, rather C depends on these factors. As seen earlier, we can assume that the capacitor is like a water tank of a given capacity. For example, imagine that this tank has a capacity of 500 liter. So whether we connect it to a half HP motor or 1 HP motor, whatever the motor is, doesn't matter at all. The capacity of this is fixed at 500 liters. So whether you fill it to half of it, fill it to 1/4 of it, fill it to 3/4 of it, how much ever is the water filled, it doesn't matter at all. The capacity is fixed. Same here. Even though we write C as Q by V, we are not defining what C depends from here. Rather, what C depends on these factors given here. So we saw that capacitance is equal to epsilon naught A by D. Let's assume that instead of having air between the two plates, suppose we have some other medium between two plates. That is, if we insert a dielectric between two plates, then capacitance should change. To understand how it changes, let's recall what is relative permittivity, which is same as dielectric constant K. By definition, this is given as permittivity of the medium by permittivity of free space. This is definition of relative permittivity. It's done in the theory classes. So from here, we can say epsilon for any medium is equal to K into epsilon naught. Recall that this K is not the same K what we wrote in Coulomb's law. In Coulomb's law, we wrote F is equal to K Q1 Q2 by R square. The K there was equal to 1 by 4 pi epsilon naught. So that K and this K are not same, they are rather different. So keep that in mind. Therefore, the capacitance in presence of a medium will call as C suffix M. So C suffix M is a capacitance in the presence of a dielectric. So recall what to say for air. It's in this form. For any medium, the form modifies now. It becomes epsilon for the medium into A by D. But this epsilon for medium is equal to K epsilon naught A by D. This factor here is the capacitance in free space. Therefore, what we get is capacitance in any medium, which is C suffix M, is equal to K into capacitance in the free space. So this is the relationship between capacitance when dielectric is present between the two plates and capacitance of a free air between two plates. We can also define K from here also. So from here K is equal to Cm by C. So I can say capacitance or dielectric constant is a ratio of, as given here, this K is a ratio of capacitance with the dielectric by capacitance with air as the dielectric, or with just air as the medium. So this is the form required here.